Hi, Mick McQuaid here. Welcome to the second half of our course, iste780 Data-Driven Knowledge Discovery. Today is day 11, and today there will be 3 recordings. The first one, this one, will talk about model selection and some criteria for choosing the best model. The next video will go over a couple of shrinkage methods, which are ridge regression and the lasso. And then the third one will be on dimension reduction methods, primarily principal components regression, but also partial least squares. So let's get going. So we have this linear model, familiar by now, linear model. And we have a couple of reasons why we might want to do something different than simply least squares to fit this model. Prediction accuracy is one, and model interpretability. And there are several different approaches that we can use to get a better fit. One is subset selection, that's what we're going to talk about here, and then the others are shrinkage and dimension reduction, which I'll talk about in the next 2 videos. So when it comes to subset selection, we basically have 3, or maybe you could say 4 methods that we're going to look at. And then we have about 3 or 4 criteria that we're going to use to choose the best model. So the first one to talk about is the most impractical one, which is best subset selection. So here's the algorithm for best subset selection. And like all of the algorithms, it's basically got two main parts. We've got some way of plowing through the models with the various predictors up to p possible predictors. And then some criteria, which we'll talk about after we talk about these 3 or 4 methods, some criteria for choosing the best among them. Now, the reason that I say that best subset selection is impractical is because we wind up with 2 to the p possible models. See here, reduce the problem from one of the 2 to the p possible models. Now, if we have a very small number of predictors, that's fine. And if we have a very small number of predictors, we can choose the either use RSS or R squared. Remember, RSS is what we want to minimize. That's the residual sum of squares is the error we want to minimize, and R squared we would like to maximize. That's the proportion of variability that's explained by the model. And if we've got 2 to 10 predictors, best subset selection isn't a big problem. But somewhere here they'll mention, if p is equal to 20, then we have about 1 million possibilities. And if p is 40, that comes to over 1 trillion possibilities. So whether it's their claim that the textbook authors make is that it's computationally intractable. But there's an additional problem, which is that it's not interpretable if you have a huge number of predictors. Well, here, look at this as an example. Right here, we had 10 predictors here, and the best model was clearly either with about 3 or 4 predictors. Actually, in this one, it's going to turn out to be possibly up to 6, but that still leaves us quite a few irrelevant predictors. That's really the big problem is irrelevant predictors. The least squares model may have irrelevant predictors, and it may not be able to tell us that those are, in fact, it most certainly cannot tell us that some of the predictors are irrelevant. So we need some way to figure that out. So the other thing that we can do is stepwise selection, and we can either proceed forward or backwards in stepwise selection. So forward stepwise selection, we keep adding predictors up to p, potentially up to p predictors, and running the regression or whatever model fitting technique we're going to use for each one of these. And so we just add the one that works the best. So this is a greedy method. It simply takes the way forward that looks the best. And that's not necessarily the best. So it reduces the possibilities. Instead of fitting 2 to the p models, we're going to fit this many models, 1 plus p times p plus 1 over 2 models. So instead of, for example, for p equals 20, instead of fitting 1,000,000 models, we would fit 211 models. Is that right? Let's see, p 4, 24, 10, 210. Yeah, okay, yeah, 211 models. Yeah, this looks reasonable. So so we pick the best variable going forward, and here's a little discursion on how it is not guaranteed to find the best model. So, and that's because it's a greedy method. It takes the best next step, and the best next step isn't necessarily the optimal next step. One nice thing is that we can use it when p is greater than n, when n is less than p. For a lot of online web-based stuff, this is the situation that you're in. You have a huge amount of data on each customer, but you don't have very many customers. So you would like to be able, or each session, let's say, not necessarily customer, each session, you might have a huge amount of data and not very many sessions or not very many customers. So it's worthwhile to have this procedure available, even if it's not optimal, simply because it's physically possible to do it in cases where other methods might not be possible. Okay, so and backward is just the opposite. It's the same thing, except that we just take away one predictor at a time, and taking away one predictor at a time, and we take away the one that takes the least away from the model. So this also, of course, is not guaranteed to yield the best. This is also a greedy procedure. Now, a more interesting thing, and they don't really spend much time talking about it in this book, but the idea of after adding each new variable, also then removing any variables, add a variable and remove the worst variables that you already have. This kind of approach is actually, I think, pretty popular. It's certainly implemented in software so that it's easy to do. So this is actually I think, a third approach that's worth mentioning. Okay, now for each of these, so we have these algorithms for forward, backward, and best, and each one of them mentions a criteria. And so here are several criteria that are almost the same. Let's take a look at the equations for these criteria. The equations, okay, so here's the equation for C sub p, and just if you just glance at that and then glance at the Bayesian or the Akaki information criterion, it looks like almost the same thing, except that we have sigma hat squared in the denominator here. I think that's the only difference. And here's the Bayesian, which has log n in this part. That's the only difference. R squared is a little bit different. Adjusted R squared is a little bit different. This is the same as R squared, except that we have degrees of freedom calculated in here, so that if we add unnecessary variables, there's a penalty. So this is the most typical of these. These authors are not very crazy about it because it lacks any kind of theoretical justification. But people do it, I can assure you, anyway. This is the most common of these four methods, but they all basically penalize extra. The whole idea is to penalize the inclusion of extra irrelevant variables, and these are just four techniques to do it. And they keep saying it's beyond the scope of this book for each one of these, proving why. So I think it's relevant to know that CP, AIC, and BIC all can be proven to be optimal. Adjusted R squared can't. It doesn't. There is no proof associated with that. and those proofs are beyond the scope of the book anyway. So that's, oh, God, I almost forgot about validation and cross-validation. So here's a number of other methods that we can use. So we talked previously about using cross-validation approaches in the last chapter. And here's validation set error and cross-validation set error. And you can see that the results are extremely similar to the Bayesian information criterion. They give very similar results. These models here from 4 to 6 predictors have almost the same level. The 6 are slightly better here than the 4 is, but not much. And in fact, I think there's a suggestion here that that you use the one standard error rule, and this would actually, in the case of the either the validation or the cross-validation approach, which we talked about before, that would actually lead us to this. It would lead us to the model with 3 predictors because of Occam's razor. So the idea of Occam's razor is the principle that if 2 explanations are equally effective, choose the simpler explanation. And this is a pervasive principle. It's named after William of Ockham, who probably never actually heard of it, but for some reason he got his name associated with it. It's called Occam's razor, OCCAM. So the idea that we prize parsimony or prize simplicity as a virtue is what leads us to choose the three predictor model. And the rule here, the one standard error rule, it tells us how much worse it can be before we stop preferring, how far up we have to go for any of these criteria, how far we have to travel up here before simplicity ceases to be an important factor. Okay, so that's it for subset selection and choosing the optimal model. And be sure to watch the other recordings for the shrinkage methods and dimension reduction methods.